We have already discussed that in high velocity metal forming, we give high strain rates for the material deformations to induce high level of stresses. Now, to impart high strain rates, we need to apply rapid loads. Now, when we consider loading, what are loadings we can apply? Loadings can be of two types. One is quasi-static loading, and second one is dynamic loading. Right? In quasi-static loading means an example that we can take is the tensile testing that we carry out on UTM. In the case of dynamic loading, an example is that a head-on collision between two vehicles. That's the case of dynamic loading. Right? So, in the case of high velocity metal forming, since we require high strain rates, the condition of loading is always dynamic. It's the case of dynamic loading. Now, how the stress distribution is different under these two types of loading, under static loading as well as dynamic loading, that's we are going to discuss. So, for that, what we are going to do is that let's take an example of a metal bar being heated at one end using a hammer. Now, while hitting the hammer, we are applying two conditions. In condition 1, we are applying a load slowly, which is nothing but a case of a quasi-static loading. Now, in the case 2, we are applying a load rapidly using that hammer, which is the case of dynamic loading. So, quasi-static means slow loading, which is case 1, and rapid loading, which is nothing but dynamic loading, which is case 2. Now, in both cases, what we are going to do is, let's consider 3 elements at any arbitrary 3 points on that metal bar, which is subjected to that load. Okay, any 3 points which have very small thickness. Now, under quasi-static loading, what happens is that all these elements are in equilibrium, in static equilibrium, which means the stresses on each of these elements will be same under quasi-static loading. However, in the case of dynamic loading, what happens is that the stresses are different with time. Now, let's say we have applied a load at the end of the metallic bar, a rapid load, a dynamic load. Right? So, say at the time t0 at section 1, there will be a stress. However, at that particular point of time, at the time t0, there won't be any stresses at section 2 and section 3. Now, consider that 1 second has lapsed, which is an exaggerated value. So, at the time t1, what will happen is that at section 2 also there will be a stress, but there won't be any stresses at section 3. Now, let 1 more second lapse. So, at the time t is equal to t2, there will be stresses at section 3 as well. So, at the initial state, there was only stress at the section 1, there was no stresses at section 2 and 3. However, with the time lapsing, with the time coming forward, each of the sections got stress influence, which means that the stress was advancing from one end, the point of application of load, to the other end with time. Now, this phenomena we can call as stress wave propagation. So, stress wave propagation happens in dynamic loading, not at quasi-static loading. So, this phenomena happens in high velocity metal forming as well. So what stress wave theory suggests that any material subjected to a load, the stress induced in the material transmits as a wave with finite velocity. Now, this velocity seems to be almost close to the velocity of sound or speed of sound. If you remember, the deformation that we induced, that particle velocities that we import was close to the velocity of sound, if you remember, right? So, the action of load is not getting transmitted all over the body instantaneously at the moment when the load is applied, but moves through the body in the form of a disturbance of wave with a definite velocity.